In this A3 tutorial, we're going to be going through a three-phase system. These are three phases. It's got 4 wires because it's got a neutral wire, and in this particular case it's an ideal neutral wire. And we're going to go through and we're going to solve for the real power, which is P, measured in watts, the reactive power, called Q, which is measured in volt amperes reactive, and the apparent power, which is called S, and that's measured in volt amps. So what we have here is we have the values or the solutions we got from the previous tutorial where we went through and we solved for currents. We had our perfectly balanced supply going into an unbalanced load, which we solved, and we got these 3 line currents. And I've plotted them here. We can see here that our phase A voltage is perfectly in phase with our phase A current, which is not surprising because it's a purely resistive circuit. And here our phase B current lags our phase B voltage by 43 degrees, and that's not surprising either because our phase B impedance is a pure resistor and some inductance, so it is not a pure resistance, so these are not going to be in phase. Similarly, in phase C, I've got a 7 ohm impedance with 650 microfarads, and that total impedance there is 8.78. Again, if you want to know where all these values come from, the previous tutorial number 1 where we solve for currents will go through and address that. Now, we need to go through and solve for these powers. And most people know that power equals VI, and if they've dealt with balanced systems, they're probably sitting here going, well, that's easy, we just go through and use root 3 for everything, because there's root 3 relationships in a 3-phase system. That holds if it's a balanced system. This is not a balanced system, it's an unbalanced system. This root 3 relationship is a gross simplification of one of these systems. It assumes everything is balanced. Because this is unbalanced, that root 3 rule doesn't apply, and we're not going to use it because it's simply not valid. We need to go through and we actually need to solve this thing originally. So let's get to it. Power is voltage times current. But that works perfectly well for DC. Like everything else you've been doing, everything you've been learning to date is a simplification of something else. And as you go through your university career and your engineering career, you'll learn that some of the stuff that you've been taught to date is true, but it's a simplification. So what we're going to do today is we're going to start unpacking some of that simplification and actually drilling down into what's happening. And likewise, what I'm going to go through today is also a simplification of other stuff, which next year or the year after you'll go through and you'll drill down further and you'll get into some calculus and stuff like that. But here we are now today. In an AC system, the real power is not just the voltage times the current. We need to factor in the angle, or specifically the cosine of the angle between the two. That is the calculation in an AC system for real power. What we call the reactive power, Q, is also VI, but it's times the sine of that angle. The apparent power, S, is simply VI. And its unit is VA, or volt amps. So let's go through and we'll go through and calculate all the power dissipated in the circuit in each of these loads, and from that we can calculate the total power dissipated in the circuit. So, power dissipated in phase A is the voltage in phase A times the current in phase A times the angle in phase A. So, the voltage in phase A, here it is here, 230 volts is applied across here. You see it here. And we're looking at the magnitudes, so 230 times the magnitude of that current times 46 times the cosine of the angle. There is no angle difference here. We can see that this has got an angle reference at 0, and this has got an angle reference at 0. 0 minus 0 is 0, so the cosine of 0. And if we go through and we do that very simple calculation, 230 times 46, the solution there is 10,580 watts. That is quite straightforward for a simple AC system with pure resistance. The power dissipated in phase B here, VB, IB, the cosine of the angle in B. Again, the magnitude of this voltage is 230. The magnitude of the current is 33 times the cosine of the angle. We can come over here and see this here. This is phase B, our 230, our 33 amps, and the angle between those two is 43. And if we go through and solve that, 230 times 33 times the cosine of 43, we get an answer that is 5,604 watts. PC is the exact same process, VC, IC times the cosine of the angle of phase C, 230 volts times 26 times the cosine of the angle here, which is 37 degrees. Now, the subject of these degrees is an area where a lot of students make mistakes. They use the wrong angle. I've seen many exams where students have gone into calculating the phase in power B, and they've used the angle up here in phase A for here. That's obviously wrong. Likewise with phase B, they will use the same one, and it's just simply wrong. If we go through and calculate this, 230 times 26 times the cosine of 37 degrees, we get a solution of 4,802 watts. So we've gone through and we've calculated that for each of the phases. The real power dissipated in these phases. The real power is how much work is done. So now we can go on and we can calculate the apparent power, the reactive power, sorry. I often confuse those in my wording. The reactive power for phase A is VA, IA, sine of that angle, and we can go through and VA times IA, which is 230 times 46 times the sine of that angle. The angle, as we've already established, the difference between these two is 0. The sine of 0 is 0. 0 times 46 times 30 is 0. There is no reactive power flowing in phase A. And that's not surprising because it's a pure resistor over here. The reactive power flowing in phase B, VB, IB times the sine of angle of B, 230 times our current, 33, times the sine of this angle of 43. We go through that and solve that, and we end up with 5,280 volt amperes reactive. 5,280 VAR, or 5.2 kVAR. QC is the voltage in phase C times the current in phase C times the angle of the difference in phase C. 230 times 26 times the sine of that angle, 37, and that is 3639 VAR. Now, this is a point where, again, like I mentioned in the last tutorial, a lot of students start making very simple, very silly mistakes. Phase B was a reactive circuit, an inductive reactive circuit, with the current lagging the voltage. So our VARs are positive VARs. However, Phase C is a capacitive circuit. The current leads our voltage. So we need to, that was often distinguished as being a minus. You need to know that the minus goes in here because of the capacitive in phase C. Here it is here. Your simple calculation won't show you that. You just need to know it and you need to stick it in. We can go through and just because we can find out the apparent power in each of these, SA, SB and SC, VA, IA, VB, IB, VC, IC. And that's 230 times 46, which is 10,580 VR. SB, again, 230 times 33, 7700, and SC, VC, IC, 6025. Now, a quick check to see if you've made a simple mistake is your S value should always be larger or equal to your P value. The only time it's going to be equal to P is if Q is 0, because this is a power factor triangle. We know what these things look like. They look like this. Here is our real power, here is our reactive power, here is our apparent power. S is always going to be greater than P, or at least equal to it, and the only way S is equal to P is if Q is 0. So we can have a quick check. SC is 6025, PC is 4802. That is larger than that. Okay, good, makes sense. Phase B, 77 versus 56. Yep, that makes sense, that's bigger than that. Phase A, 10580, 10580. They're the same, not surprising, because Q is 0. So all of our calculations have kind of passed this little test that we can have here to make sure that everything's looking okay. So we now have calculated the real power, the reactive power and the apparent power dissipated in all three of these phases. But we still haven't got the total power in the system. We need to find the total real power, the total apparent power, the total reactive power. Can we simply go through and add all of these up? The answer is yes and no. We can add all the real powers up and all the reactive powers up, but we can't add all the apparent powers up, because we're going to build up a series of, this is power factor triangles for each of these phases. And we can do that. We'll do that over here. So let's draw the power factor triangle for phase A. In the direction over here, here's PA, and that is going to be 10,580. Here it is here. We'll call that 10,580. In the reactive component, we have nothing. So that's it. That's quite simple. And SA, well, SA, using these values, is that? That's our so-called triangle. What we can then do is we can add on the power factor triangle for phase B. So let's do that. Phase B has got 5,600 watts, which is roughly half, give or take. So we'll make that half a length. That's probably to about here. Close. PB. Now we have a Q of B of 5.2, which is roughly the same. So let's, that value there, it's about one of my knuckle lengths, it's about up here somewhere. And that is SB. Now we can add on the power factor triangle for phase C. 4,000, which is a bit less than that, so we'll draw it to about there. And we'll call that PC. And we can see here that the reactive power in phase C was 3,600, but it's in the negative direction because it's capacitance. It's in the opposite direction of inductance. Now, it's probably opportune to say you will often see in some books, you'll see these drawn this way, where the reactive component Q, the positive, are going that way, and Q negative is drawn as being down this way, which is the way that I'm drawing it. You'll also see some where this is the other way around. And there's an argument for one and there's an argument for the other. For the purposes of these calculations, it makes absolutely no difference whatsoever. The important thing to note is that the Q for an inductive circuit has got to be the opposite polarity as a Q for a capacitive circuit. That's the important thing to remember here. So, we've established our QB here of 5,280 var, and we've got our QC of minus 3.6, which is roughly, give or take, 2/3. So we'll come down here like this, QC. So that is SC. So there is our three power factor triangles all drawn, and we're going to add them all up. And we can see that the resultant, to get from here, our origin, to our resultant here, we can complete that power factor triangle for the whole lot like this. Along these dotted lines. Our dotted lines are, if I draw it in dots as well, S, T, PT, and QT. Now that we've drawn our power triangles down here, we can go through and we can effectively use calculations to confirm that this is right. So what we can see here is the total real power is PA plus PB plus PC. 10,580 plus 5,604 plus 4,802 is 16.23. PT is PA plus PB plus PC, 16.23 kilowatts. QT up here, QA plus QB plus QC is 0. Plus 5,280 plus minus 3,639 1641 1.64 kVR. Now, to find the total apparent power, we just can't add up that plus that plus that. It doesn't work that way. We've now got a power triangle in total using these values here. This value here is 16.23 kilowatts, and this value here is 1.64 kVAR. We now have it in rectangular form, and we can simply do a polar conversion on that. Polar of 16230, comma 1640 of 16,312 at an angle of 5.78. Despite the fact that we have a theta on phase A of 0, a theta of 43 degrees lagging in phase B, and a theta of 37 degrees leading in phase C, our total angle overall, this angle down here, is 5.7. We can find out the total power factor in our system the cosine of that angle of 5.78, which is 0.997. And is it a leading or a lagging power factor? It's inductive. The capacitive does not completely cancel out the inductive, so that is a lagging power factor. Our total system overall would have a lagging power factor of 0.997, which is fairly close to unity, obviously, because we see here that the effect of our capacitance has almost negated our inductance, but not quite at this particular frequency. Here we have our total power, apparent power overall, 16 kVA. Our total power factor, 0.997. Our total real power, 16.23 kilowatts. And our total reactive power of 1.6 kVAR. What else is there to do? The only other thing we could possibly do would be to go back and re-look at our phases and think, well, what was the power factor in our individual ones? The power factor of this angle here is 0. The cosine of 43 would give us the power factor of this phase, and the cosine of 37 would give us the power factor of this one here. That is how you find the real power, the reactive power, and the apparent powers for each of the phases in a three-phase system, as well as the overall power. At no stage did we use any root 3s in these calculations, because these calculations are correct for an unbalanced system. This is not a balanced system. Thanks for watching.